I'm Bill Merton, designer, manufacturer, and owner of Mert Skis. In this video, I'll talk about torsional rigidity and its importance in the design of skis for use on firm surfaces, otherwise known as ice. If you've raced or ski a lot in the Northeast, you've probably heard that torsional rigidity is the critical property governing a ski's ability to hold on ice. That's true, but have you ever wondered what torsional rigidity is and why it's critical? I'm going to keep this discussion qualitative at first. I'll save the equations for the second part of the video. That way, if you're not into the math, you can just quit, but at least you'll have some idea what this torsional rigidity stuff is all about. Essentially, torsional rigidity is resistance to twist. I'm holding a piece of PTEX, which is pretty flexible stuff. If I hold it at the ends and rotate my hands in opposite directions, I produce twist. This piece of PTEX is pretty easy to twist, so it's not very torsionally rigid. A more torsionally rigid material, like a 2x4, would be much harder to twist. But wait a second, you say. The 2x4 is much thicker than the PTEX. You're right. In its mathematical definition, torsional rigidity is the product of a material property and a geometrical term. So why is torsional rigidity so important to a ski's ability to hold on ice? To answer this question, we're going to do something called a thought experiment. What is a thought experiment? It's an experiment that you perform in your mind. What it allows you to do is to alter parameters important to the experiment in ways that are not physically possible or plausible. In my thought experiments, I tend to exaggerate the parameters to the point where they are absurdly small or large. What results is usually an insight into the question that is not usually evident when the parameters are close to normal. So here's my thought experiment on torsional rigidity and ice. Imagine this piece of PTEX is a ski. It has very low torsional rigidity. Next, I've attached a ski boot to the ski with hot glue bindings. Now imagine that this table is a ski slope, inclined to the horizontal at some angle. Look at what happens when I apply a torque to the ski using the ski boot. The tip and the tail hardly go on edge. Not even Michaela Schifrin could make that ski hold on ice. Let's go in the other direction. Imagine a ski with infinite torsional rigidity. The response of the tip and tail would exactly mimic the torque applied to the ski boot. The angle of the tip and the tail to the snow would be exactly the angle of the boot to the snow. Why don't ski manufacturers make skis with infinite torsional rigidity? Then we could all ski on ice. It's not that simple. Not all skiers have the ability to ski on skis with very high torsional rigidity. The problem is that without precise edge control, the skier will tend to catch edges, which is unpleasant at best. On to the next question. What factors produce high torsional rigidity in a ski? Remember that I said torsional rigidity is a combination of a material property and a geometrical term. Let's tackle the geometry first. At any given point along the length of the ski, the cross-section is essentially a rectangle. Rectangles have width and height. The height or thickness of the ski contributes the most to the geometric component of the torsional rigidity. But if the height is too great, it will be too difficult to bend the ski into reverse camber. The proper strategy here is minimize the width so that the emphasis can be put on the thickness. Regarding the material properties, the important thing to know is that the maximum stress occurs on the outside of the rectangular cross-section, as shown here. The maximum stress runs in directions of plus and minus 45 degrees to the longitudinal axis of the ski. So what we want to use for the top and bottom layers is a very strong material. Carbon fiber in an epoxy matrix is much stronger than fiberglass, and it's much lighter too. Both carbon and fiberglass fabrics come in biaxial weaves that align the fibers at plus and minus 45 degrees to the longitudinal axis. Since the only function of the core is to hold the top and bottom layers apart, almost anything that will bond to epoxy will work. K2 has used foam. Hexel used aluminum honeycomb. Heads XR1 used fiberglass struts with only air in between. Most companies use wood. If you're looking to buy a pair of skis off the rack, about the only things you'll be able to determine are the core and top and bottom materials. You'll have to trust that the manufacturer has used fabrics with a biaxial or quadraxial weave. Biaxial weaves have fibers oriented at plus and minus 45 degrees to the longitudinal axis. Quadraxial weaves have fibers oriented at 0, 90, plus 45, and minus 45 degrees to the longitudinal axis. Good custom ski manufacturers should be able to use a combination of different weaves to give you exactly what you want. How do you judge torsional rigidity in the ski shop? The answer is you probably can't. It's not as simple as bending a ski to judge its stiffness. At Mert skis, we have a fixture we use to hold a ski at its waist and apply torque to either the tip or the tail. We then measure angular deflection. Most ski shops will not have this equipment. The best way for you to judge torsional rigidity is to get out on the slopes and experiment. That's it for the qualitative portion of this video. Now I'm going to throw some equations at you. If that's not your cup of tea, it won't hurt my feelings if you turn this video off now. Torque and angular deflection are related by this equation, where T is the applied torque, J sub T is the torsion constant for the section, G is the shear modulus, phi is the angle of twist in radians, and L is the length of the section. The torque is the applied force causing the twist, times the distance of the force from the center of rotation. For circular sections, J sub T is equal to the second moment of inertia. This assumes that plane cross-sections remain plane when twisted. This is true for circular sections and circular annuli. This is not true for rectangular cross-sections, which most closely approximate a ski. However, the second moment of inertia is a good approximation to J sub T. So for a rectangular cross-section, we will approximate the torsion constant by this equation, where B is the width of the ski and H is the thickness. When we substitute the expression for J sub T into the equation relating torque and angular deflection, we get this equation. Here we see that for the same torque, if we increase J sub T, we decrease phi. Furthermore, if we increase B, we decrease phi. However, if we increase H, we decrease phi much more. Thus, the ski designer's strategy to increase torsional rigidity should be to use as narrow a width as possible and increase thickness to compensate. But the ski designer must also keep in mind the effect of thickness on flexural stiffness. Finally, the quantity J sub T times G is known as torsional rigidity. As claimed previously, it is made up of a geometrical property, J sub T, the torsion constant, and a material property, G, the shear modulus. This is the end of the quantitative portion of this video. I hope that what I've presented here has helped you to understand the importance of torsional rigidity in holding on ice and how ski manufacturers take advantage of geometry and materials to increase torsional rigidity. A link to this video may be found at mertskis.com.